Okay guys, so in this lecture we'll be continuing on seeing the concepts of full-filled orbital and half-filled theory. Okay, so let's get started with. So actually we were seeing in the last lecture the cause of stability, in which we mentioned a term called exchange energy. So exchange energy for a, so let's see the exchange energy. So exchange energy for p shell or rather p subshell. So if you look into it, so exchange energy first of all is for degenerate orbitals only. Okay, and for p subshell we would be having, this is the p subshell. So let's say it is partially filled with three parallel spin quantum number, or other three parallel spins. Okay, so due to Hertz rule we are uh, uh, giving them the same or parallel spins. Okay, so what will happen is the exchange energy is defined as the shifting of electron from one of the p subshells to, or p orbitals to, another p orbital. So in this case total energy released because of exchange between the electrons in different orbitals of p subshell, so total energy released would be minus 3e. Okay, so e is the energy released for one exchange. Okay, so amount of energy released in one exchange pair of electron of degenerate orbital is called exchange energy. Amount of energy released in one exchange change pair of electrons of degenerate orbital is called exchange energy. Okay, so it always carry a negative sign. Negative sign. Okay, so next actually let's look at pairing energy. So pairing energy is nothing but, if we have something like this, let's draw a d orbital, and in the d orbital we have 1 2 3 4 5 unpaired electrons with the same spin. So these is d orbital with all our degenerate orbitals. Okay, and total exchange energy in this case would be, so total exchange energy could be, one of the electrons here can exchange with 1 2 3 4 places. Okay, this electron can exchange with 1 2 3. Okay, so 4 plus 3, plus this electron can exchange with 1 2 places, and at the last this electron can take or change itself with only this electron. So total exchange energy would be minus 10 e, if e was the exchange energy for one exchange pair. Okay, so now if we look at this d orbital which has 10 electrons, okay, so 10 electrons would be 5, first 5 would be filled with parallel spin, next 5 would be filled in all the degenerate orbitals. So here how many pairs are there? Total number of pairs here are 5. So let's say the pairing energy released due to the formation of one pair would be p. So the total energy released due to the formation of rather not let me put it like this. So when we get we actually get the energy released due to the exchange between the electron pairs, and this much energy is required to actually pair up the electrons. So this is not released, this is actually required. Okay, so total energy in this case would be minus 10 E for the plus half spin. Okay, minus 10 E for the minus half. So in other terms we can write for all the electrons with this and for all the electrons with this notation, and 5p is required for pairing up of electrons. Okay, so amount of energy required to pair up two unpaired electrons in an orbital of a subshell is called pairing energy. So amount of energy required to pair up two unpaired electrons in an orbital is called pairing energy, and it always carries a positive sign. Okay, so let's now take another example of, let's say, chromium 24. So the configuration would be AR18. So let me write the square brackets for AR18, and then we have the configuration as 3d5 and 4s1 due to half filled and partial filled theory. So had it been we had written the configuration as 3d4 and 4s2, we would have the configuration or the filling up of orbitals in a subshell as something like this. This is 4s, this is 3d, 4s2, so it would be something like this, 1 2 3 4. Okay, so and if we have 3d5 and 4s1, then it would be something like this, again 4s1 and 3d5. So the configuration would be here 1 2 3 4 5 and 1. So here this is obviously incorrect. So here we are actually saving on a pairing energy, and we are also having more exchange energy than the previous one. Hence here this actually validates our rule of, or our theory of, half filled and fully filled orbitals. Okay, so let's actually see for this. So what is the aggregate value of exchange energy and pairing energy here? So if we drive this for calculating the exchange energy, so exchange energy would be nothing but 1 2 3 and 4 here, because this electron can also be exchanged with this one. So the exchange energy would be 1 2 3 4 here. Okay, so 4 plus, for this one we have 1 2 3, 3 plus 2 plus 1, that should be 10 minus 10, and we have also a pair. So total energy would be, exchange plus pair would be minus 10 E plus 1p. And for this case, let's actually see for exchange energy. Exchange energy would be 1 2 3 4 5. Okay, so for this it would be 5 plus 4 plus 3 plus 2 plus 1, that would be minus 15 E. And how many pairing energy? 0 pairing energy. So obviously total energy, which is exchange plus pair, is greater for this one or the second configuration, hence this would be preferred. Okay, so hence it is clear that a higher value of exchange energy and pairing energy contributes more to the stability of a particular electronic configuration for a atom. Okay, so let's actually take some examples in seeing more on exchange energy and pairing energy. So suppose we have copper 29, so configuration would be nothing but AR18, then we have 4s1 and 3d10. We have to calculate the exchange energy and pairing energy in this case. So first case could be obviously we can have 4s2 and 3d9. Okay, so in that case we would have 4s2 here, 3d9 here, 1 2 3 4, 4s2 here and 3d9 here. So what is the total energy? Total energy would be what is the exchange energy here? Exchange energy would be, for this electron we would be having 1 2 3 4 5, plus for this one we have 1 2 3 4 plus 3 plus 2 plus 1. Okay, and similarly this was for the plus half spin. You have to also count for the minus half spin. For the minus half spin we would be having 1 2, for this one we would be having 1 2 3 4, for this one we would be having 1 2 3, so plus 2 plus 1. So this is for minus half, and how much pairing energy? It would be 1 2 3 4 5, 5p would be required. Okay, so total energy in this case would be minus 25e plus 5p. Okay, and what about the case when we have configuration second one as 4s1 and 3d10? For 4s1 3d10 we would have something like this. This is 4s1, this will be 3d10, 1 1 2 3 4 5 6 7 8 9 10. Okay, so total energy would be now pairing energy for this, or rather for plus half spin, would be, for this one we would be having 1 2 3 4 5 up to 1. Okay, for minus half we would be having 1 2 3 4 4 up to 1. And how much pairing energy would be? It would be 4p. Okay, so total energy in this case would be, so this is the total energy for this case, and for total energy for this case would be again minus 25e plus 4p. So this energy is lower than the above energy, hence this would be more stable. That's why we would be choosing 4s1 and 3d10 as the final configuration. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing multiplicity, and we'll be seeing some questions on finding out the spin multiplicity of several configurations. So till then, good luck and goodbye.